Welcome to today's central exercise session. Today we'll be discussing sheet number 2, and as usual, you're welcome to ask questions during the central exercise session. The chat for questions can be found on chat.tum.de. So we're using TUM's Rocket Chat system, and please use that channel here, MA9711-CE. That's the module number minus CE. As usual, the chat will be moderated. Today's moderator is Lejuri Fernandez. Lejuri, would you introduce yourself, please?
Hello everybody, and welcome from my side as well to the central exercises of sheet 2. So my name is Lejuri Fernandez. I am a postdoc at the chair of Math Finance at TU Munich, and I will be today the moderator. So whenever there is like an easy question, I'll try to answer immediately. Otherwise, there will be a break after each exercise, and we can forward them to Michael, and then he will provide an answer and a nice explanation. Thank you.
Okay, thanks a lot. So let's start with problem sheet number 2 right away. Let me share my screen so you can see what I'm going to write. So on sheet number 2, we have 3 different problems for the central exercises today. The one main topic here is systems of linear equations and solving those systems of linear equations. So basically today we're going to deal with systems of linear equations and Gaussian elimination as a method of solving those. Now,
excuse me, Michael, like your voice kind of like got quiet.
Give me a second. Is it better now?
No, yeah. Now we can hear you.
Okay, great. So that seems to happen sometime with the headset I have. So whenever that happens, just please pipe up anytime. Thanks. Okay, where was I? Gaussian elimination. So today we're going to see some examples of Gaussian elimination. And before we go into that, let me mention one question that is asked fairly often is, you probably know other methods for solving systems of linear equations from school or from some other courses that you took. And of course, these methods are usually all valid. Still, I recommend you get used to Gaussian elimination mainly for 2 reasons. The first reason is, in my experience, this method is the most systematic and the least error-prone method. So students that use Gaussian elimination and practice Gaussian elimination are less likely to make errors during the computations. Again, that's just my personal experience. Your mileage here may vary. The second reason is we'll use basically the same procedure that you see in Gaussian elimination. We'll use that same procedure in other places as well. The reason for that is, of course, there is some kind of equation solving going on in the background in a more or less well-disguised way. But the procedure that you see on the front will be more or less exactly the same as Gaussian elimination. So it helps to get some practice using that method, because we will definitely make use of it later on in other contexts. Okay, so let's start with exercises. We first do exercise C21. That's basically an easy introduction into Gaussian elimination. And then it gets a little more complicated in the following exercises. In C22, we're solving a larger system that even includes a parameter. And in C23, we are reversing that idea and we're designing systems of linear equations that have a given property in terms of having a given solution space. So let's see. We'll start with exercise C21. In C21, we're given a system of 2 linear equations in 2 variables. And that system is 3x1 plus 4x2 equals 18. And x1 plus x2 equals 5. And the first task is sketch the lines defined by each of those 2 equations into a coordinate system. So what you can see here is this equation here That is a relation between the x1 and x2. And if you interpret x1 and x2 as a point in two-dimensional space, so in the plane R2, then of course you can draw all points that satisfy this equation. And then the same way you can draw all points that satisfy that equation here. And in that case, the set of points that satisfy these equations turns out to be a line. So that's what we do in part A. We just sketch these two lines here. Now, let's see. I need a coordinate system first. That should be sufficient. So here's going to be x1. Here's going to be x2. And let's see. We have 1, 2, 3, 4, 5, 6. That should suffice. Same thing here. 2, 4, 6. Yeah, almost. So let's draw these two lines here. We'll start with this line here. I'll do this in orange. If you already know that that is a line, one of the easiest ways to draw that line is probably to just find 2 points that are on that line and then connect those. So in that case, almost always the easiest way is to set one of those 2 coordinates to 0 and then see what the other has to be. So for example, if we set x2 to 0, like here's a 0 then we have 3x1 equals 18. If 3x1 equals 18, then of course x1 has to be 18 over 3. That's 6. So this point here, 6 and 0, that is on that line defined by the first equation. That point fulfills the equation. And second, we're looking for a point that also fulfills the equation where x1 is 0. Now, if x1 is 0, then this part here becomes 0. So we need to satisfy 4x2 equals 18. So that's x2 equals 18 over 4 or 9 over 2 or 4.5. So that is here. And that means we have to connect those 2 points. So that's the point 9 over 2. 0, 9 over 2, of course. And now we just need to connect those two. Let's see. Almost. Okay, so that is the line defined by that first equation. And the second equation here, that's even easier. Again, if we set x2 to 0, then it just says x1 equals 5. So that point here, 5, 0, that is on that second line. And if we set x1 to 0, then it says x2 equals 5. So that point here, 0, 5, that is on that second line. So let's connect those two as well. Oh, that was not good. Let's try again. Better. Okay, so any point on one of those lines solves the corresponding equation. And for the equation system, of course, we need a point that solves both equations at the same time. So we need a point that is on both lines at the same time. And that point is exactly where those two lines intersect, of course. So this point here, that will be the solution. And that point is, at least roughly, from my sketch, I would say that is 2, 3, or somewhere in the vicinity of 2, 3 at least. Okay, if you try to use a ruler, maybe your sketch is better than mine, and you should exactly get to 2, 3. And we'll verify this in just a minute. Okay, that was B actually. So we already did B, where we are asked to guess that solution, and then verify that our guess is correct. And let's do that as well before I'm taking the first questions. So we want to verify that 2, 3 is actually the solution. Our guess is 2, 3 is the solution. And let's verify that. And to do that, we just substitute the point 2, 3 into both equations. and see whether they both satisfied. So for the orange equation, that means we have 3 times 2 plus 4 times 3. And that is, well, that is 3 times 2 is 6, and 4 times 3 is 12. So that's 6 plus 12, that's 18. And in fact, 18 is the correct right-hand side. So that's right. And for the second equation, well, we just get x1 plus x2. So that's 2. Oops. 2 plus 3. And that is 5. And again, 5 is the right-hand side of the equation. So that's correct as well. Well, that means we have actually found the solution to that system graphically. And as you have already seen, hopefully, that involves quite some work. And it also was not that clear what the solution is because my drawing was not that good. Your drawing might be better, but imagine the solution was not something like 2, 3. Imagine it was something like pi over 7 and 5e to the third or so. You'd probably not be able to solve this exactly using a graphical approach like this one here. So that's usually not what we'll do, but it still helps to have in mind what the geometry of these things look like. And indeed, we will make use of that geometry later on when we design equation systems. So before we go on with applying Gaussian elimination to that system, let's see if we have any questions already.
Yes, indeed, we do have a question that it says in video chapter 019, around minute 1345, the distributive law is applied even though we technically haven't shown that property to be applicable yet.
Sorry, I didn't get that. What is applied there?
The distributive law is applied even though we technically haven't shown that property to be applicable yet. Yes. And then what he wonders is, why is this allowed?
So for calculations in R to the n, we will assume that this law is indeed applicable. We're not going into all of the details in that case.
Okay, then there is another question that it says, what if you label the axis the other way around, meaning that y is equal to x1 and x is equal to x2? Would that still be correct?
Again, I didn't quite get that. Could you repeat that?
Sorry, yeah, it says like, what does it happen if you label the axis on the other way around? So meaning that y is equal to x1 and x is equal to x2, and whether it still would be correct.
Yeah, that would still be correct. Of course, the drawing would look differently. Basically, it flips around if I do that, but that's it. It would still be correct.
Perfect. So far, these are the questions that they were on the chat.
Okay, great. So let's go on with Gaussian elimination then and see if there's any more questions after that. Okay, part C. Transform the system into a tableau. So a tableau of the form, we have some left-hand side in the tableau. We'll usually denote that by A and some right-hand side B. What we do for the tableau is first we need to make sure that all the coefficients associated with some x are on the left-hand side of our equation system. And all the constants are on the right-hand side of our equation system. Now that is already the case here. So if you look at that system once again, it already has the desired form. Like this. So all the x parts are on the left and all the non-x's are on the right. And that means we can just write down the tableau by you taking the coefficients in front of the x's here. And we put that on the left of the tableau where the A currently is. The only thing you have to take care of is, of course, the coefficients in front of these are ones. Please don't write zeros in that case. So the tableau basically becomes, we have 3, 4 on the first line and then 1, 1 on the second. And the right-hand sides, we have an 18 and a 5. We just draw a line here in the middle like this to separate the right-hand side from the left-hand side part. So that is what the tableau looks like. And let's also do part B right away, part D, sorry. And part D is to apply Gaussian elimination to that system of linear equations. And for the intermediate steps, it asks us to, again, do a sketch that illustrates these intermediate steps. Now, Gaussian elimination procedure, there's a number of choices that you can make on the way. So usually the elimination process itself is not unique. You could do it the way I do it. You could do it differently. And your result may on the surface look differently as well. But the solution set that you get should, of course, be the same. So whatever method you choose will yield the same solution set if done correctly, of course. So let's do Gaussian elimination here. We take this Tableau, sorry, write that down again. And the idea of Gaussian elimination is basically to obtain something that we call Echelon Form. That means we want to have the left-hand side matrix in a kind of triangular form. We want to have zeros basically below that diagonal, and maybe with some longer steps if the matrix happens to be non-quadratic. So what that means is for each row, beginning from the first row, we choose the leftmost non-zero element. We designate that as a so-called pivot element. And then we do steps that transform that equation system, keeping the solution space the same, but in a way that we obtain zeros below that echelon, below that pivot element. Let me show you by example. That's probably much easier than talking about it. So in this case, I could start by designating this element here, the leftmost non-zero element in the first row. I could designate that as my first pivot element. And then I'd have to do transformations, elementary operations, to obtain zeros below that. So I would want that one to go away, basically. To make life a little easier, I opted to do a step in between that. Specifically, I'm going to swap those two lines first. In an equation system, the order of equations does not matter at all, so you're free to rearrange the lines as you see fit. And I hope you're going to see why I did that in just a minute. I'm just going to swap those two. Put the second row in the first place and the formerly first row in the second place like this. And then again, I'm going to look for a pivot element. So I'm going to choose in the first row the leftmost non-zero element. That's this, oops, sorry, this one here. So that's my first pivot element. I'm going to use that to produce zeros below that by doing elementary row operations. These elementary row operations, basically there's a handful, 3 of them. One is to swap any rows, we just did that. The other one is you can multiply any row by a factor as long as it's not 0. Of course, multiplying by 0 would basically make an equation vanish. So if you do that, obviously you're losing information. You don't want that. So 0 is not good, but any other factor is fine. You can multiply any row by any factor other than 0. So that's fine. And the third operation is the one we use most. And that is, we'll take any 2 rows and then add a multiple of the first row to the second and replace the second row by that combination of the original second row plus the multiple of the first one. And we're going to use that operation, basically adding and subtracting equations from each other to produce the intended 0 down here. And what we need to do here is we're going to operate with that first row here, specifically with that pivot, with that 1 here. And to obtain a 0 here, what we need to do is we need to subtract the first row times 3 from the second row. So we subtract 3 times the first row. And when I do these operations, I'll always make small notes on the side indicating what I'm going to do. So like this here, minus 3 times 1. So that Roman numeral here, that is intended to mean the first row of my system. And my advice to you is do the same. It makes it a lot easier to catch errors later on. So if you find your result is not correct, then if you go back and try to locate your error, it's a lot easier to remember what you intended to do if you have these little side notes here. And also in the exam, it will help your corrector see what you intended to do. So even if you did it wrong and got a wrong result, maybe there's still a few points that you can get on your correct intentions. If there's no help for the corrector to find out what you intended to do, then of course he will have to assume you didn't know what you were doing. And that always looks bad. So these little notes are always a good idea, and I'll try to do those. But let's see what happens. We did not change the first row at all, so we can just copy that. And the second row changes in the following way. We subtract 3 times 1 from 3, so that's 3 minus 3, and that's 0, which was the intention, so that's good. And then we have 4 minus 3 times 1, 4 minus 3, that's 1. And please don't forget to do that operation on the right-hand side as well. Here we have 3 times 5 is 15, and 18 minus 15 is 3. So we get a 3 here. And as you can see, we still have our pivot here. Now we have zeros below that pivot, so that operation was successful. And also you can see that we have obtained Echelon Form. So basically below the diagonal, we just have zeros. On the last row, there's also one non-zero leftmost element, and this is this one here. So this last row also has a pivot element. If that was a 0 row, it wouldn't have a pivot element. We'll see examples of that later. But here we have 2 pivot elements. And what we can do now to obtain the solution is we just solve the system backwards. So we start with the last equation. The last equation is that row here. So the corresponding equation, we just use those variables again. Remember, the first column corresponds to x1, the second column corresponds to x2. So that last equation here, that reads x2 equals 3, or 1 times x2 equals 3. So we already know the value of x2. And then let's go to the first equation. This one here. And that reads 1 times x1 plus 1 times x2 equals 5. We know x2 already, so we can substitute that here. And what we get is x1 plus 3 equals 5. And of course, that can be solved for x1. That's 5 minus 3, that is 2. So the solution we get in the end is x1 equals 2, x2 equals 5, or if you want to write that in the form of a solution set, we'd say that is the point 2, 5, and only that point. Oh, sorry, not 5, by the way. That's my mistake. It's not 5, it's 3, of course. Yeah, so it's 2, 3, not 2, 5. And luckily, that's just the same thing that we got in our guess. So actually, our guess 2, 3 was correct, and we could even verify that doing Gaussian elimination. So that's how that procedure works. Finally, a quick sketch of those intermediate steps. Basically, there's only one. Swapping these two equations, like here, it doesn't do anything to the geometry. What you could do is, of course, you could change the color of the lines, but the lines will be the same. In that second step here, we actually change the equations. So that changes the whole system a little. We keep the first one. So let's catch that one again. Again, I'll have x1 here, and I'll have x2 up here. Let's see, 1, 2, 3, 4, 5, 6. 2, 4, 6. 2, 3, 4, 5, 6. 6. So what we have is, again, that line through 5, 0, and 0, 5. That was the equation that we did not change. And then there's this new equation that just says x2 equals 3. That's easy. Let's just this line here, x2 equals 3. And again, the intersection of the two, of course, did not change. Again, we have this intersection here at 2, 3. Okay, that completes the first problem on our sheet. What questions are there concerning that first problem?
Yeah, so basically, like there are, maybe we should kind of like clarify how to do the switching of the rows is not really necessary. But it's kind of like an ordered way to do the things, like it's a tidy way to do things. There were a lot of questions saying, is it really necessary to switch the rows? Can we really sort of switch the columns? Or in the exam, would you also like for us to mark each row with a Roman numeral? And if so, should they remain constant even when changing rows? So maybe clarify this.
Okay, I try, yeah. So first, the switching of rows is of course not necessary. You can do without switching rows. Let me quickly demonstrate how that works to see, maybe then you get an idea of why I did that. So I could also use this 3 as my first pivot element, and then try to, literally, could you switch off your microphone? I'm getting echoes. Sorry, thanks. And then try to get zeros below that 3. So what we would have to do then is we have to subtract 1/3 of the first row from the second. And what that gives us is, well, the first row just stays the same this time. And let's see if I can get this right. 1/3 times 3 is, of course, 1. So we have 1 minus 1, that's 0. Then we have 1 minus 4 over 3. So that should be minus 1 over 3. And then we have 18 over 3, that is 6. So 5 minus 6 is minus 1, right? And of course, you also get Echelon Form now. You again have 2 pivot elements. The only difference is I had to use fractions when I did that computation, and that led to fractions here. That's not much of a problem in this 2x2 system, of course. I'm done anyway. But imagine that was something like a 5x5 systems. And I really don't like doing fractions if I can avoid it. And having this 1 here as the pivot element, as I did here, that helps me avoid these fractions. And that's basically the only reason I did that. That other method works just the same, and you'll get just the same solution if you do that. So you can do that without switching rows. The one place where you have to do that is if there is a leftmost non-zero element that is not on the first row, but in one of the subsequent rows. So you'll always have to look for the leftmost non-zero element in all the rows and then get that in the first place, or the line that you're currently doing, to use as the pivot element. Yeah, so that you get this staircase structure. That's when you really have to do a row swap. Otherwise, that's optional. You can do it if it makes computations easier. You don't have to. Second question was, I think, concerning the Roman numerals I'm using. So usually these Roman numerals here, these always refer to the rows in the current step. I'm not keeping those numbers the same. So in this step, by row 1, by the Roman numeral 1, I always refer to this first row here. In that second step, a 1 would then refer to this row, which is the same here. But here in that step, take that one for example. In this case, a 1 would refer to this row, whereas this row I would refer to as a 2. And after I switch, I then refer by 1 to this row. So I always mean the first, second, third, and so on row in the current matrix. So these labels kind of change if I swap rows. I find it a little confusing to try and keep the labels as they were in the beginning, because I kind of have to keep all the switches in my head, which I don't want. And the idea of those labels is not to be mathematically precise, but just to give you a hint of what's going on. And I think it's easier that way. And I remember you also asked about switching columns, so flipping columns around. You could do that as well. If you do that, basically that means you are relabeling the variables. So you're interchanging the roles of x1 and x2, and you either have to keep track of that and undo the labeling in the end, or you kind of have to invent new names in the end to make clear what you did. Because if you're switching columns and then also switching the names of the variables, then of course, in the end, you won't get the right result anymore. So if you do that, you have to keep track of your switches and undo those in the end. I'm usually not going to do that. I find it doesn't make things easier, but just more confusing usually. So I hope I answered all the questions. Did I forget anything?
Well, there are still more questions that they were coming while you were still explaining.
Yeah, go ahead, ask.
Yeah. Okay, there is one question that I forgot in the beginning, that it said, why is it possible to subtract or add equations to the system of linear equations?
I didn't quite get that.
I think I don't really get it either. Like it says, why is it possible to subtract or add the equations of the system of linear equations?
Oh, okay, yeah. I hope I know what you mean. Let's see. So let's just take these equations here as an example. These two here. So if we have these two equations here, basically what we're doing in the first step is we're subtracting the, in this case, the second equation. I'm not going to rearrange those now, 3 times from the first one. What does happen here? Well, basically, the solution space of that system is combined of all points that satisfy this equation and also this equation. So if we have a point that satisfies both equations, then of course that point will also satisfy the new equation that's obtained by taking the first row and then subtracting 3 times the second row. That yields a new equation. Our points satisfy this one, our points satisfy this one, so they also satisfy 3 times this second one. So they also satisfy this minus this, obviously. Okay, so any solution to that system of 2 equations also satisfy the new equation. On the other hand, if I have this new equation plus my old one, this here, then it's easy to obtain the original equation back using the same idea. I can just take this one and add it back to the new first equation. And then I obtain the old first equation. So again, any point that satisfies this one and this one will also satisfy any combination of these. And one of the possible combinations is to just obtain this first old one. So in total, what we get here is any point that satisfies these 2 equations also satisfies those 2 new equations and vice versa, meaning the solution set of these and this is exactly the same. That doesn't change through this operation. Okay, the one thing that would of course changes is multiplying an equation by 0, for example. Yeah, if we multiply that by not 3 but 0, then this equation would vanish, and that of course would change the solution set. Well, basically, that's the idea of these elementary operations. That's a number of operations that doesn't change the solution set. That hopefully answers the question if I got it correct.
Okay, there is then another question that it says, could you make an example for the connection between the number of solutions and the rank?
We'll have that in 2.2. So if you could just wait a few more minutes and we'll see that in 2.2.
Perfect. Then it says, did I have one? Wait a second. Yeah, can we also change the sequence of the rows even if there are more than 2 equations? If yes, how can we do that?
So the question is, if I have more than 2 equations, can I still reorder the rows? And the answer is, of course, yes, you can. The order of the equations doesn't matter for the set of solutions. So you can reorder them in any way you want.
Then there is another question that it says, do we have to put brackets around the Tableau in every step? So yes.
So usually, yes, we put brackets around the Tableau just to make sure you actually recognize it as a Tableau.
Okay, then
Again, that helps the corrector see what you're doing.
And then it says, do the lines of the intermediate steps always have to meet in the same point? In this example, x1 equal to x2 equal to 3.
So the lines of those intermediate steps, as I said, the solution space does not change through these intermediate steps. So the lines always meet in that same point, or generally the subspaces generated by the equations meet in the same, more generally, subspace. In this case, it's just a point, but of course it could be something else. But that solution space will not change. So in all intermediate steps, the intersection, so to say, is the same.
Okay, then there is another question related to problem 2.5, but like these problems, they are solved in the tutorials.
Yes, so please defer those questions to the tutorials. If we have time at the end, I'll happy to pick those up, but we probably won't.
Okay, I think now I read almost all of them. So
good. So I'd say let's start 2.2 to see how the rank is connected to the solution space. Now exercise 2.2. That's basically just a larger system of linear equations, 3 equations, 3 variables. The one thing that's different is we now have a parameter in there. And the question is, what is the solution set depending on the value of that parameter, and how does it change in size? So basically, what's the rank and how is that related to the solution space? Now, that system, let me write that down once again. This is x1 plus x2 plus lambda x3 equals 1. And then we have 1 plus lambda x1 plus 1 plus lambda x2 plus 2x3 is 2. And finally, lambda x1 plus x2 plus x3 equals 1. So these are the 3 equations. And I can, again, just solve it by Gaussian elimination. So I'm putting that in a Tableau. And the Tableau is, for the first row, we get 1, 1, and lambda on the left-hand side and 1 on the right-hand side. For the second row, we have 1 plus lambda, 1 plus lambda, and 2 for the left-hand side and a 2 on the right. And for the third row, we have lambda, 1, and 1, and a 1 on the right-hand side. So I'm going to solve that Tableau. First thing I'll do is I'll locate a pivot element. The leftmost non-zero element is in column 1, and there is one in the row 1. That's a 1. And that's probably the easiest I can get, so I'll just keep that. And now I want to produce zeros below that 1 here. So what do? Well, to get a 0 here in that place, I have to subtract 1 plus lambda times the first row. So I'll do that, minus 1 plus lambda times the first row. And here I just subtract lambda times the first row. So let's take a quick moment to reflect on why we actually are allowed to do this. There's basically 2 things that we need to watch out for. I already said we must make sure to not multiply an equation by 0. Now, what happens if lambda is 0? It's a parameter. Any number in R is fine, so 0 could also be one of the possible parameter values here. So what if we have lambda equals 0? What happens here? Is that multiplication actually allowed? And of course, it is in this special case because we're not directly multiplying an equation by lambda and then replacing it by that multiple. But what we do is we're replacing this equation here by that equation minus lambda times 1. And if lambda happens to be 0, then we just keep that equation that we have. So it doesn't go away. What we cannot do is multiply, for example, this row 1 here by lambda and then just keep that new equation. Because that might mean if lambda happens to be 0, we have just destroyed an equation. So if we have to do something like that, we will always have to make a case distinction. And the same is true if we divide by some expression that contains lambda. So in this case, we're lucky. We multiply by lambdas and lambda expressions like this one. It doesn't really matter whether these expressions are 0 or non-zero, we can always do that. But we could not divide. So if we, for example, would use this here as a pivot element, then we would have to do something like add 1 over lambda of this line to some other line. And in that case, again, we have to make a case distinction because lambda could be 0 and then 1 over lambda would not be defined. So what we'll do is we just pay attention to those two things that could go wrong. We make a quick note when we assume something about the lambdas, and then we pick up those extra cases in the end. But it's important to keep that in mind and to not lose those extra cases. Okay, as I said, nothing will go wrong here. So let's do the computations. We just copy the first row like that. For the second row, we get 1 plus lambda here minus 1 plus lambda times 1. So that's a 0. Here we have 1 plus lambda minus 1 plus lambda times 1. So same thing, that's also 0. And the last one is a little more complicated. Here we have 2 minus lambda times 1 plus lambda. So here we get 2 minus lambda 1 plus lambda. That's a little more complicated. And for the right-hand side, we again have a 2, and here we have 1, so that's 2 minus 1 plus lambda. And for the last row, here's lambda minus lambda times 1, that is 0. Here we have a 1 minus lambda times 1, so that is going to be 1 minus lambda. And here we have a 1 and a lambda, so that is 1 minus lambda squared. And for the right-hand side, we have a 1 here and a 1 here, so we get 1 minus lambda again. Okay, that looks nice. Now, next thing we have to do is we have this pivot here. We obtain zeros here. Now we have to go to the second column. See if there's a pivot in the remaining 2 rows in the second column. And indeed, there is this element here that could be 0, but probably it's not. So if lambda is 1, then that would be 0. And we would not have a pivot, but if lambda is not 1, then that might serve as a pivot element. This here is a 0, so that can't be used as a pivot. And now we have a case where we actually have to swap rows. We have to get the pivot in this place here. So that's what we're going to do next. We're going to swap these 2 rows. And that way we obtain 1, 1, lambda, and 1. Then here we have, let's see, 0, 1 minus lambda, and 1 minus lambda squared, and 1 minus lambda. And here we have 0, 0, and 2 minus lambda times 1 plus lambda. And here on the right, let's see, 2 minus 1 is 1. So we have 1 minus lambda here. Could simplify this a little. Okay, so that should be our new system. And we have a pivot here. We have a possible pivot here. And as you can see, we already have zeros below that new pivot. Here, that column is already fine. So that is echelon form. And that means we're done. Whatever is in this last place here, whether 0 or not, doesn't change the fact that this is an echelon form. So this is the best we can get in terms of a Gaussian elimination. And now, of course, the question is, what is the actual solution of that system? And to do that, we'll have to look at the possible cases once again. We do backward substitution. So the first thing that we have to do is we have to solve for x3 using this equation here. And this equation, that's equal to 2 minus lambda, 1 plus lambda times x3 is 1 minus lambda. And we can only solve that for x3 if we can divide by this number here. And that we can do if that number is not 0. Now, we can simplify that a little. So that expression here, that is 2 minus lambda squared. And as you can easily verify, that's the same thing as 1 minus lambda and 2 plus lambda. Just compute the roots of that expression. Okay. So the zeros, the roots of that expression are 1 and minus 2. So whenever lambda is not 1 and minus 2, we can divide by that expression and everything's going to be fine. Otherwise, we might run into troubles. We'll see. So now we finally arrived at a case distinction. Let's first do the easy case, and that is the one where we can divide. So that means lambda is not equal to minus 2 and also not equal to 1. In that case, we can divide by that expression. So 1 minus lambda times 2 plus lambda is not 0. So we can solve for x3. And what we get is x3 is 1 minus lambda divided by 1 minus lambda 2 plus lambda, and that is 1 over 2 plus lambda. And then we can use that, go back.
Excuse me.
Yeah.
Sorry, I think like students have spotted that there might be a mistake on.
Yeah. Where did I go wrong?
So like when you have the last Tableau.
This one here, yeah.
Yeah, like I think like the last row.
This one.
Yeah, and no, well, the constant component, so 1 minus lambda. That
yeah.
one, I mean, they are spotting, and like since I was taking care of the questions, I didn't really.
Yeah, you didn't. Yeah.
Yeah. Yeah. So I mean, it's
they think it's not correct. That should be the same as this one here, because I swapped around. So this is 2 minus 1. That's 1 minus lambda. I think it's correct.
Yeah, it's correct.
Unless I made the error before already. So let's just go on with that. Hoping it is correct, I'll recheck that later. And of course, if you find the actual error, then please just let me know, either in chat or just write me an email. And I'll correct that in the solutions later. Okay, let's assume this echelon form is right for now. Then we can just use that to solve the rest. So we have x3. We can now use this equation to solve for x2. And this equation, let's write that down once again. That is 1 minus lambda. Let's see, 1 minus lambda x2 plus 1 minus lambda squared. X3 is 1 minus lambda. And now if I'm using the X3 here, substitute that here, then I get 1 minus lambda X2 plus, let's see, 1 minus lambda squared over 2 plus lambda equals 1 minus lambda. So that means X2 is equal to, let's see, I have to divide by 1 minus lambda and move that part here to the right-hand side. So this divided by 1 minus lambda, that's obviously 1. So I get 1 over this 1 minus lambda squared is the same thing as 1 minus lambda 1 plus lambda over 2 plus lambda. And I also divide that by 1 minus lambda, of course. So that is 1 minus 1 plus lambda over 2 plus lambda. And that is 2 plus lambda over 2 plus lambda. That's my 1 minus 1 plus lambda over 2 plus lambda. So what I get is, let's see, 2 plus lambda minus 1 minus lambda. So that leaves me with 1 over 2 plus lambda. That looks nice. That seems to be right. Okay, so that's my X2. And finally, let's take on X1. X1 corresponds to this equation here. So that's X1 plus X2 plus lambda X3 equals 1. X1 plus X2 plus lambda X3 equals 1. So we can also solve that right away. X1 equals 1 minus X2 minus lambda X3. And again, I'll substitute the results I already have. So this is 1 minus my X2 is 1 over 2 plus lambda. My X3 is lambda over, where did I have that one? Here it is, 1 over 2 plus lambda. So lambda times 1 over 2 plus lambda. And again, let's try to simplify that. Then what we get is the 1 is the same as 2 plus lambda over 2 plus lambda. Then we have minus 1 over 2 plus lambda. And then we have minus lambda over 2 plus lambda. So we get 2 plus lambda minus 1 minus lambda over 2 plus lambda. Or that is simply 1 over 2 plus lambda. So finally, the results are X1 is 1 over 2 plus lambda. X2 was also 1 over 2 plus lambda. And X3 was 1 over 2 plus lambda. So actually that seems like a nice solution. I'm pretty convinced that's right. So set of solutions, we can abbreviate that a little by taking out that factor 1 over 2 plus lambda. We have the same in every coordinate. And just to make sure that that set of solutions consists of just one single point, and that point is dependent on the parameter lambda. So that's not a set that contains one point for every lambda, but what I do is I prescribe one certain value of lambda, and then this is the solution set. For all cases where lambda is neither -2 nor 1. And let's just quickly have a look at those cases before I take questions and before we take a little break. So we have to take care of these other two cases. The first is, what if lambda equals -2? In that case, let's go back to the first place where we actually needed this assumption. That was here. So when we solved here for X3, we needed the assumption that lambda was neither -2 nor 1. Everything before that did not require that assumption. So this step here, that last echelon form, that is still valid. So we can use that and just substitute our lambda value in that one. We don't have to redo all the Gaussian elimination steps. Okay, so this one is valid for lambda equals -2. And that means we can just substitute that. And we get the following echelon form, 1, 1, -2. Well, just let me write that in color, -2. So that's the lambda. I just substituted. Then we have 0, 1 minus lambda. So that's 1 plus 2, actually. That's 3. Lambda squared is 4. So yeah, 1 minus 4, that's -3, sorry. And the right-hand side is 1 minus lambda, so that's 3 again. And here on the last row, we have 0, 0, and then 2 minus lambda times, so you will remember that -2 was the root of that expression. That means we know that is 0 without doing any more new computations. And the right-hand side is again 3. So that is the echelon form for the case lambda equals -2. And what you will hopefully notice is this last row here. That contains a left-hand side of 0 and a right-hand side of 3. So basically that is the equation 0 equals 3. And of course, that is a contradiction. That can never be true. So in that case, our solution set is the empty set. So what you'll also see here is, in this case, we have these two pivot elements, but no pivot element in the last row on the left-hand side. So the rank of the system is now 2. And if I add the last column, then I get a new pivot element here. So that would change the rank to 3. And that is an indication that it cannot be a solution, right? So the rank of our left part here, that is 2. Whereas before, you remember that we had this system here with that pivot, and if that is not 0, and it was in this case here, then of course the rank would be 3. And that means we get a unique solution. Last case, let's quickly do that as well. Case lambda equals 1. Now again, we did not use that assumption that lambda was not equal to 1 up to that very first case distinction. So we can again use that same echelon form here. So let's copy that once again if I can. I can't. Let me just copy again. Okay, so again, this is valid also for the case of lambda equals 1. And that means what we get is 1, 1, 1, 1, 0, 0, 0, 0, and 0, 0, 0, 0. So now we get 2 0 rows even. One of our pivots is left. This other pivot, this one here, this also became 0, so it's not a pivot anymore. And that means the rank in this case now suddenly drops to 1. But if I add the right-hand side, that just adds zeros down here. So no new pivot elements are added to those last 2 rows. And that means the rank stays at 1. And there actually is a solution. Well, what is the solution in this case? Again, remember the variables correspond to the columns, sorry. So what that means is we have a pivot element in the column corresponding to x1, but no pivot element in the other 2 columns. So what happens here is that these other 2 variables are free variables then. x3 is a free variable, x2 is a free variable. Those may take on any value, and for any combination of those two values, there is a corresponding x1 value such that we get a feasible solution. And of course, x1 then has to satisfy this first equation here for any given value of x2 and x3. So we take that, solve it for x1. That's again 1 minus x2 minus x3. We did that already. And this time we don't have values for x2 and x3 because those are free variables. And that means for any combination of those, we get one solution point. So the set of solutions is composed of all points that look like this: 1 minus x2 minus x3, any x2, any x3. And those take any real number as a value. Or to rewrite that a little, we can also split this in the constant parts and then the x2 parts and then the x3 parts to make the structure a little more clear. And the only constant part here is as 1. So we have 1, 0, 0 plus x2 times the x2 part. Here's an x2 and here's an x2. The first is minus 1 times x2. The second is 1 times x2. So it looks like this. And x3s. Again, we have an x3 here and an x3 here. So we have a minus 1 here, a 0 here, and a 1 here. Okay, so that's how the solution space in that case looks like. Remember, the rank of the system was 1. We have 3 variables, 3 columns in total. So that means rank 1 means 3 minus 1 free variables. And that's what we get here, 2 free variables. Okay, let's take a few questions and then we'll take a quick break for an announcement of the Student Council.
Okay, so I think like you might need to explain again why, what's the reason of doing the distinction of lambda equal to -2 and lambda equal to 1, because they're having like a bunch of questions related to that.
Mm-hmm. So that's hopefully easy to answer. Remember that here was the Echelon form that we arrived at. And what we're doing now is we're solving the system backwards as we usually do. So we start at this equation here. And this equation looks like this. So to solve that for x3, what we have to do is we have to divide by this expression. And you notice this expression contains lambdas. So what could happen here is that expression could actually be 0. And if it is 0, we cannot divide by that expression. Yeah, dividing by 0 is just not allowed. So we need to find out what are the values of lambda so that this expression is 0. And we do this by simplifying a little. That's what happens here and then here. So this is the same expression. And here you can easily see what the roots are. So this here, this part becomes 0 if lambda is 1. This becomes 0 if lambda is -2. So for all other values, lambda not equal to -2 or 1, we can divide by that expression. That's the first case. And then, of course, we'll have to look at those 2 other cases, lambda equals -2 and lambda equals 1, where we cannot divide by that expression and see what happens. And that's why we do this case distinction here. And that's also where we get our cases from. So that does not happen during the Gaussian elimination step, but only during this backwards substitution step where we actually solve the equation system. That's where we need this case distinction. Other questions?
Yeah, so there is now another question that it says, what's the required condition for getting the 2 free variables? Was it that the right side had 2 0 columns, or that our 2 last equations were 0 equal to 0?
So we're looking at this case here where we have 2 free variables. Basically, the condition is what we have here is one pivot element, this one here. And that pivot element is in the column that corresponds to x1. And columns with a pivot element correspond to non-free variables, to bound variables. This column here, and also this column, does not contain a pivot element. They're not 0 columns, but these are not pivots because they're not leftmost in their respective line. Yeah, in these lines here, there is no pivot. And that means those columns correspond to free variables. Columns without a pivot correspond to free variables. So that's why we have these two free variables here. And the number of free variables can easily be seen by the rank. So here we have one pivot, meaning the rank of that system is 1. And we have 3 columns. Number of columns minus the rank is the number of free variables. But it doesn't yet tell you what the free variables are. You can identify those by looking for the non-pivot columns, like these two here. That should hopefully answer it.
Then there is a question that it says, so how can we put in the case extinction and calculate with them if we cannot actually divide by them?
So that's why we do the case distinction actually, right? Now in the first case, we're restricting ourselves to values of lambda where we can actually do the division. And that means that case and the solution we get is only valid if lambda happens to be non-equal to -1 or non-equal to to +1. Sorry. So any real number but these is fine, and then we can do the computation. And for the other two cases, we proceed in the same way. So we just treat those cases separately and look at what happens then. And then we covered all the possible cases for lambda. These two special cases plus the, so to say, the non-special case, which covers anything but these two numbers. I hope that was the question.
Yeah, like maybe I would like to ask students that whenever like they find the answer, please to somehow send the sign, maybe a thumbs up or something, so that we can really know that it's clear. Then there is another question that is, can you show the equation for finding x1 again?
For finding x1, the first one. So this for x1, oh sorry, x1, this is this one here. So we get that from the Echelon Form. Here's our x1. So here's the pivot at x1, and that means we can solve that row for x1. And that's exactly what we do here once we know the values for x2 and x3. And then we can solve for x1 and then substitute the values for x2 and x3 in there. Hopefully that was what you wanted. Otherwise, please just ask again.
Yeah, and then there is like, how is the rank defined?
The rank, that's easy. The rank of a system of linear equations is just the number of pivot elements in Echelon form in the Tableau. So we just count the number of pivot elements, and that is the rank.
Why are there two solutions for lambda? I think this was already answered.
Yeah, there's not two solutions for lambda. So there's two special cases for lambda, because for these special values, we cannot divide by that coefficient here in front of x3, and that means we have to get to our solution space in a different way. At first general approach, in case 1, that does not work if lambda takes on one of these two special values, -2 or +1.
Can you explain the solution for x2 again?
The solution for x2, same thing as for x1. You take the second row, this one here. We do this right here. That is that second row. And then you substitute the x3. We know that x3 already. You arrive at that equation and you just solve that for x2. And we can do that, remember, because we know lambda is not equal to 1. We can safely divide by this factor here. Okay. I hope we covered the most important questions.
I think so, yeah. Yeah.
Good. If there's still open questions, just post to chat. We'll have a look at those afterwards. And now, as I said, we'll take a quick break for. Yeah, sorry.
A little comment, like for the ones that they are using the chat in the Zoom, like they should move to use the chat in the Zoom platform. So
yes, please. So if you're using the Zoom chat, we will not answer questions on Zoom chat. We can't monitor two systems at the same time. Please use that chat here, chat.tum.te, and use this channel here. It's also linked on our Moodle page to ask your questions. We'll be happy to answer the questions there. Okay, and now for a quick break and an announcement of the Student Council. Stefan Kovacevic is here to make that announcement. So I'll just give the screen to him.
Yes, thank you very much. Hi everybody. I'm Stefan. You may already know me from the Student Council welcome event, but if you don't, I'm the Student Council speaker together with Alex. And yeah, I'm here to talk to you about the semester speaker or the election, which will take place next Monday. Just so you know what a semester speaker is, there are actually two semester speaker for your intake, and those will be elected fellow students that will represent your intake. So they will be like or act as a communication point between you, the student council, and the faculty. So if you have any concerns, any problems, questions, ideas, anything, you will go to those people, and they will make sure that they're communicated to the faculty, and will try to find a solution. So who can become a student or semester speaker? Actually, every one of you. The only rule is that you're part of your intake. And yes, if you're interested, sorry, I didn't even put on the presentation. Yes. And if you're interested, you can write us an email at fss@tum-sum.com with your name and why you want to become semester speaker. And yes, the election, as I already told you, is next Monday, also during the mathematics course. And I will ask all of you to be there, since you're voting for somebody that is representing you and giving your intake a voice. So I guess you want to feel comfortable with the person you're voting on. And yes, if you have any questions, you can always write us an email, or you can post your questions in the Rocket chat. I will be here some minutes to answer them, but not for too long. So if you have any questions, just write at fss@tum-sum.com. And see you next week.
Okay, thanks a lot. So let me also add, it's really important to vote for one of these semester speakers. Those are a particularly important role in these difficult times, because we cannot get in contact directly. So it's really important to have one or two persons that are able to speak for you as a whole and represent you. Okay, let's go on with exercise 2.3 then. Hopefully we can at least cover most of that. So in 2.3, the question here is to come up with systems of linear equations, specifically with 3 equations and 3 variables that have a given set of solutions. And the first set of solutions that we are asked to come up with is simply the empty set. That one should not be too difficult, I hope. The simple idea here is to just come up with equations that can never be satisfied at the same time. We've already seen such equations, something like 0 equals 3, so that would do it nicely. Formally, if you need to come up with 3 equations and 3 variables, of course, you can do something more sophisticated if you want to. For example, you could always take the same left-hand side, like x1 plus x2 plus x3, and then come up with a first equation that says that sum is 1, and then just use the same left-hand side again.
Sorry to interrupt
Yeah?
you, but I cannot see your screen in case you are.
Oh yeah, I'm sorry, you don't see my screen. I forgot to switch on screen sharing again. My bad. Thanks for interrupting. Now that should work, hopefully.
It does. Yeah.
Okay, great. So you didn't miss a lot, as you can see. So as I said, you can just use the same left-hand side. And then if you want to produce a contradiction, so something that doesn't have a solution, just use a different right-hand side. So just use 2 for the second equation. And now it says, well, the sum of x1, x2, and x3 has to be equal to 1. Well, it can't be equal to 2 at the same time. There is no solution that would satisfy this. And as a third equation, let's just add one more contradiction and say, well, same sum is equal to 3. Okay, so that's just not possible. And if you apply Gaussian elimination, you quickly end up with 0 rows on the left and non-zero entries on the right. So you get a contradiction as we've seen before. Okay, so something like that. Empty set, that shouldn't be too difficult. Part B. Part B asks for a solution space of the form lambda times 1, 1, 1 with lambda in the interval from 0 to infinity. That's probably a little harder. So that space is like half of a line. And that's also something, if you have a little experience, you'll see that, that's also something that you can never get as a solution of a system of linear equations. So in this case, the answer is there is no system of linear equations that has a solution like this. It should become more clear why that is the case in the videos that you're hopefully currently watching. But let me still give you an argument of why this cannot work. So the first thing that we'll notice is the point 0 is included in that system. So all zeros, this vector here, that is included in S. Well, what does that mean? That means if I have an equation that looks like, say, a1 x1 plus a2 x2 plus a3 x3, that's one equation in my system. And some right-hand side, let's say 0 is the right-hand side. And I substitute that 0, 0, 0 in there. What do I get? When on the left-hand side, I get 0 plus 0 plus 0 equals a 0. So the only way the system, the solution can actually work is the right-hand side has to be 0. If that's non-zero, then we'll never get an equation system that has this solution space because it cannot contain 0, the 0 vector. Okay, so that means the right-hand side of our SLE has to be zeros. So once we know that, that means the equations in our SLE have that form here, but with the right-hand side of 0. So let's assume we have one of these equations, a1x1 plus a2x2 plus a3x3 equals 0. Let that be one equation in the SLE, an arbitrary one. And assume there is a system of linear equations that actually does the job, so has this set of solutions. Then let's take another solution. For lambda equals 1, we get the point 1, 1, 1. That is also contained in S. And if you substitute that, that means we get IA1 plus A2 plus A3 is 0. And that could very well be the case. Yeah, just need to choose your A1, A2, A3 correctly. But if that is the case, then of course we can multiply this equation by any number that is non-zero. So for example, we could multiply this by -1. And then we would get minus A1 minus A2 minus A3 is also 0. Or in other words, A1 times -1 plus A2 times -1 plus A3 times -1 is 0. But what that means is that this point here, -1, -1, -1, that obviously solves that equation. And of course, that argument holds for all the equations in the system because I did not make any assumptions on the A1, A2, A3. So that would hold for all equations simultaneously. And that means this point is also in the solution space. But if you look at the solution space again, you'll notice that our S is all non-negative multiples of 1, 1, 1. So the vector -1, -1, -1 is not even contained in that space. But here it says, well, if it contains 1, 1, 1, it also must contain -1, -1, -1. So that's a contradiction to the definition of S. And that means we cannot get a solution set of that kind for any system of linear equations. No SLE has a solution set like this S here. So there is no SLE that satisfies this. Okay, that's the first two parts. Let's quickly see if there's any questions to those before we move on to the last part.
So, yeah, sorry. Yes, there is a question that it says, why can't you work with the roots to get a system of linear equations for 2.3b?
Sorry, why can't I work with the roots to get a system for what?
Like, why can't you work with roots to get a system of linear equations for 2.3b? So root of x1 equal to root of lambda and so on.
Root of x1 equals to root of, okay, so what that lambda does here in that context is it describes the set of solutions that we have. So if you look at that definition here, this one here, what that means is we're taking all points that can be obtained in this way. And lambda is between 0 and infinity, so any non-negative number. So what we get here is any non-negative multiple of that vector 1, 1, 1, including 0. So basically that lambda is a way to describe that, well, half or part of a line that we get. It doesn't really have to do much with the system of linear equations. And that's probably why I don't understand that question well. Also, taking roots is usually not necessary in the context of linear equations. Remember, there is no other exponent than 1 or 0. Yeah. So for linear equations, we only have x1 to the power of 1, x2 to the power of 1. There is no squared or to the power of 3 or something like that.
Yeah, it's again, Michael, your microphone went a little low.
I really need to do something like that. Maybe I should buy a new headset. Working again?
Yeah, it works.
Okay, sorry.
Then, like, there is, so if lambda would have been defined for all reals, it would have a solution. Then there is,
Yes.
Yeah. So
and we'll see that in part C, by the way.
And then we said, like, can we have lambda on the right-hand side? For instance, x1 equal to lambda, x2 equal to lambda, x3 equal to lambda.
In that case, what would the value of lambda be? So of course you can come up with a system of linear equations that has a parameter, like we did in 2.2. That was a system of linear equations that has a parameter. That can also be on the right-hand side, not just on the left-hand side. But that's different from what we have here. So in this case, the lambda is really only used to describe a set of points, and we want a system that has that set of points as a solution. And for a parameter, we'll have to make a decision on the value of that parameter. And then for each value, we can say something about the system and its solution space. So what we want is not a set of systems that each have one particular point as their solution. But we want one system that has a set of points as their solution. And that's the difference here. We want that line or half of a line as a solution of one system. And we don't want an infinite number of different systems that each have a different point as a solution. That's what we did in 2.2. And that's a huge difference. Not quite sure that's what you meant.
Yeah,
Otherwise, please
like,
just ask again.
Yeah, or give us some signs that it's correct or not. Whether it's clear or not. Then, like, maybe you might need to explain again, like, why, like, when you multiply it by -1, it doesn't work. Like, of course, if you would have multiplied it for any positive number, it could have worked. But the thing is that, like, I mean, like, maybe you explain it if I were to.
Yeah. So the trick here is basically you take one possible solution. And you get this equation here, and you can multiply this by any number you want. And again, that does not change the feasibility of the equation. The trick, of course, is that the right-hand side is 0. Yeah, so that does not change at all, whichever number I use to multiply with. And what I want to obtain in this way is I want to show that there are solutions, or that this is a solution. This implies that the system must have solutions that are not contained in S. So that's what I want here. And that's why I multiply this whole thing by -1 to get this. And if that is feasible, then of course that is feasible as well. So this holds, that means this holds, and that implies this holds. And that in turn implies that this is a solution, which it can't be, because that contradicts our assumption about S. If I multiply that with a positive number, of course I can also do that. I can multiply this whole thing by 2, and then I'm getting something like, then I'm getting something like 2a1 plus 2a2 plus 2a3 equals 0. And that would imply 2, 2, 2 is a solution, but that's not a contradiction. 2, 2, 2 is included in the set S that is requested in that problem statement here. So I need a negative number. Basically, -1 is one possibility. I could also take -pi or -17 or -42, whichever you like. I hope that clarifies the question.
Okay, it says, like, can it also be argued that it is not a feasible solution because a vector exists as a solution just by depending on a point? So let me repeat it. Can it also be argued that it is not a feasible solution because a vector exists as a solution just by depending on a point?
A vector exists as a solution depending on a point. I'll have to admit I don't get that question. Maybe you can discuss that in chat afterwards.
Well,
maybe you can try to clarify that one, and we take it afterwards.
Yeah, that would be,
or we just
great.
clarify that in chat. Or again, if that doesn't help, of course, you're welcome to ask at the tutorials again. I'll also be there.
Then there is another one. It says, if there is a solution that exists without our parameters, then there exists a contradiction. There is a solution that exists without our parameters, then there exists.
There is no parameter in that system. Again, that lambda is a means of describing the solution space. And we'll get to know other means of describing the same solution space that don't formally require that lambda. So there is no parameter in that system. The system that we would have come up with does not require a parameter. And we don't want the parameter here. We just want any system that does that. We don't want a number of systems that do the same. I'm not asking for the class of all possible systems that do have that solution space. I'm just asking for one. So don't bother with a parameter.
Can you explain once more how this solution set is not possible?
So again, assume that solution set was possible, then we can know two things about that. The first is we can easily find out that the right-hand side of any equation in that system needs to be 0, because 0 is contained in that set. That's the first step. So we know the right-hand side is 0 here. Once we have that, again, assume there is a system, and let's take any equation in that system, like this one here. Then we know this point is contained in the set. So we can substitute that in the equation, and we get this here. So if there is a system that has this solution, then the coefficients of every equation must be connected in this way. Now, if that's the case, then we just these steps here to infer that -1, -1, -1 that also satisfies that same equation. That also satisfies this equation necessarily. So that is also contained in our solution set S. But the solution set S that we get in the problem statement does not contain this point. So what we show is whenever we have this point, we also need to have this point. And if only one of these is contained in our S, which is the case here, then that cannot be the solution space of a system of linear equations. That's what we're proving here. Basically, if you watch the videos of this week, what we do here is we show that the set S does not have the linear subspace property. So it's not a linear subspace, and that means it can't be the solution space of a system of linear equations.
What if you square x1, x2, and x3 and then draw the square root? Then there are just positive solutions. Why can't you do something like that?
I'm not squaring anything, and I'm not taking absolute values either, by the way. So what that amounts to is basically taking absolute values. A linear equation system cannot have that. So you only have x1, x2, x3 multiplied by some constant. That's the only thing that can happen in these equations. All the other equations that you could come up with are nonlinear equations. And of course, there might be nonlinear equations that have this sort of solutions, but we're not talking about those. We're only concerned with linear equations. And there's no squares and no square roots and also no absolute values in these. So that's why I can't do that.
Would there be a solution if 0 is excluded?
Would there be a solution if 0 is excluded? No. Again, that's not a linear subspace. Then the proof is just becoming a little harder. Basically, you can show that you can't exclude 0.
Then there is a question that it says, how do we know lambda is not a parameter? I think this is what it means.
So again, lambda is not a parameter because it does not appear, a parameter is a constant that appears in the system of linear equations, like we had in C22. That's not the case here. That is not a constant because it runs through that whole interval. And for a parameter, the idea of a parameter is that for every prescribed value of that parameter, we have a new system of linear equations or a new point or something like that. And that's not the case here. We have a whole set of points and we want our system to have that whole set as the solution at the same time, not depending on a parameter. If you compare this to 2, you will see that for every value of lambda in 2, we have a different system of linear equations and a different solution. And at least in the general case where lambda is not -1 or -2 or 1, that solution consists of exactly one point. Which point that is, of course, depends on lambda, but it's one point for every choice of lambda. And in this case, we want the solution to not be one point, but a half line. And that's the difference here. So I suggest we move on to C so that we get an idea of that. And if you have any more questions, then please just post those to chat. I'll read up on the unanswered questions later on. I'll try to provide answers. And of course, you're also welcome to join the tutorial sessions on Thursday or the Q&As on Wednesday and Friday and ask your questions there if there's any open questions remaining after that. So let's move on. C. Now, basically, that's almost the same thing as in B, but without the problems of B. So what we have is lambda times a vector, 1, 2, 3 in that case, and now lambda in R. So this space here geometrically, this is a line, and that line passes through the origin. Zero, 0, 0. Yeah, again, lambda equals 0 would yield 0, 0, 0, so that point is included. And in this case, we not only have non-negative multipliers, we only have the negative multipliers as well here. So what happened before in part B cannot happen anymore. If 1, 2, 3 is included as a solution, then also -2, -1, -2, -3 will be included. So that problem just went away. And now there's several ways to approach this here. What we need is we want a line in R3 as our solution space. Let's first approach this from a, let's say, systematic standpoint. So what we want is basically a solution space where the first coordinate of our solution has the form lambda times 1. The second coordinate has the form lambda times 2. And the third coordinate has the form lambda times 3. Yeah, that's exactly my lambda times 1, 2, 3. And now that must work for every lambda. For every possible value of lambda in R. So not just for one lambda, it's not a parameter, but for every possible lambda. So we must find a system that satisfies these conditions for every possible value of lambda. Now, what system would do this? Well, one thing we could do is we could just take this here and try to eliminate that lambda out of that system here. And that's, of course, not too hard to do. Because what the first equation says is basically here, x1 is equal to lambda, right? So that's what our solution must have. x1 must always be equal to lambda. So that means we can just write x1 in place of lambda. So what we get is, well, the first would just be x1 equals x1. That's not a lot of sense in that one, yeah. It doesn't really do anything. But the second one, x2 equals 2x1, and the third one, x3 equals 3x1. Okay, so what that means is x1 would be a free variable. I can set that to whatever value I want. And then the other two, x2 and x3, would follow and would form a point that is contained in my set S, and that is exactly of that form here. So what that means is I just have to reformulate that system that I just obtained a little. That equation, the first equation here, that's not really necessary. I could just throw that away. It doesn't yield anything useful. And the others I just reformulate slightly to get the desired form. So I would say that is 2x1 minus x2 equals 0, and 3x1 minus x3 equals 0. And formally, if I really want 3 equations, because the problem statement says so, then I just add something like 0 equals 0. Yeah, but that's not necessary. So these two equations here, if you solve those, if you determine the solution space of those, then you will get exactly that system here. And that system has exactly the solution space that we started with. Geometrically, what happens here is that each of these equations here in R3, those equations describe a plane. So you remember that an equation with 2 variables in R2, we had that in the first problem, that describes a line. In R3, the equivalent is a plane. So you get all points x1, x2, x3 that satisfy an equation like this, all these lie on a plane. So what we have here is 2 planes. And the solution set of that system is the intersection of those 2 planes. Well, that's a line. And that's exactly the line that we started with, this line here, because that satisfies both of these equation sets. That's because we designed them to satisfy those 2 equation sets. And that's also a different way to attack that kind of problem. You could also say, well, I want a line here, I want this line, so I need to find 2 planes that both contain this line and that intersect. So they shouldn't be equal, of course, yeah? So I just need to come up with any 2 planes that contain this line that are not equal. And then I just write the planes in this form to get my equations. I'll also include that approach in a suggested solution, so you can look that up as well. I just don't have the time to explain that anymore. So let's see, is there any last minute questions before we conclude the session?
Sorry. Yeah, well, there was a question that has been like recurring all the time. Whether it's possible to have to do quizzes in teams of 2.
So that's an organization question, right? You're referring to the quizzes on Moodle? I guess you're referring to the quizzes on Moodle. So please don't do that in teams of 2 or 3 or something. Please do those alone. The idea is to give you a chance to find out whether you actually understood the topics that we discussed in the lecture and in the exercises, because you will be responsible for also clearing the exam. That will also not be done in teams of 2. And that is why it's a good idea to do the quizzes alone. Please don't do them in teams of 2.
Okay, and then there are a couple of questions related to part C. How would we solve such a question with a coefficient that doesn't just let us equal one variable with lambda?
Basically, you can solve it in the same way. And there's a number of problems, of similar problems in the homework section. So just try the same approach. You'll see that it works. And if it doesn't work for you, then please just ask in the tutorials. We can discuss that there.
Okay, then there are a couple of organizational questions. Is there a time limit on the quizzes?
I don't really know, actually. I don't know whether they set a time limit. I don't think so. So we agreed to not set a time limit. Basically, you have a week. So from Monday to Sunday to solve the quizzes, so that they count. And again, a quiz is counted as a pass if you obtain at least 80% of the points of that quiz. So that's the time limit you have this week. But from the start of the quiz to your successful solution of the last problem, there's no time limit other than that.
Then it says the quizzes don't give you a grade bonus, right?
No, they don't give you a grade bonus. So what they will give you is, if at least 50% of the participants registered on Moodle pass each of the quizzes, then I will give you a kind of a rehearsal exam, an example exam at the end of the semester, so that you know what to expect from the real exam. So that's kind of the bonus that you get, but there's no grade bonus.
Then it says, do we also have as a lecturer in the next semester? I'm not really sure I understand the question.
So if the question is whether I'm going to do mathematics too, then the answer is probably yes. If that's not the question, then please rephrase.
We only can try the quizzes one time? Or once?
I think you can only try them once, yes.
Then there is a question that it says, could you check the first quiz again? There seems to be a mistake in question number 20.
So if you think you find a mistake in the questions, then please just post that to chat or to the Moodle forum, and I'll forward that to the quiz masters.
How much do you need to get to pass?
80% of the points are needed to get a pass for each quiz.
Well, there is more people typing, but so can you maybe explain how to find the system of linear equations for a more complex solution space, like for instance, a plane?
Well, basically a plane is even easier because you only need one equation. Again, there's more problems of that kind in the homework section. So please just refer to those. I think there's also a question where you need to get, there is a question where you need to get a plane. So give that a try. Again, the approach is the same that we just discussed. And if that doesn't work for you, then please just ask in the tutorials. We discuss that there.
Apparently they explained that the mistake, I think the mistake that they referred to the question 20 in the quiz is described in the general chat.
Okay, yeah, again, I'll have a look at that afterwards and I'll forward it to our quiz master so they can have a look at it. And we'll get your feedback in the chat.
And so far, that's it. And it doesn't seem like anybody is typing anything else.
Okay, great. So we conclude that central exercise session for today. Thanks a lot to Lajuri for moderating the chat. And I'll see you all next week or hopefully on Thursday in the tutorials. So again, if you have any questions, you're welcome to ask in the tutorials at any time. And I hope to see you there. Goodbye.
Thank you. Ciao.